In this lecture, we shall show that every permutation alpha in Sn can be written as a product of disjoint cycle. Then we shall proceed towards expressing every permutation as a product of transpositions, and then proceed towards writing the inverse of a given permutation in a symmetric group Sn. So we start here by this result, which is in the form of the theorem. Every permutation every permutation alpha in Sn is either a cycle is either a cycle or a product of disjoint cycles. Or a product of disjoint cycles. Now we do the proof of this result, and we prove this result by inducting on the number of points moved by alpha. Here we have this alpha is a permutation Sn, so this alpha may be moving or at least either zero number of points, or it will move some positive number of points, and we will make the proof of this result by inducting on the number k of points moved by alpha. So the proof is by induction. So we prove the result by induction on the number k on the number k of points moved by alpha, moved by the given permutation alpha. Now suppose if k is equal to 0, that means the initial case is that alpha does not move any point. If k is equal to 0, that is when alpha does not move any point, when alpha does not move any point. So this means that the permutation alpha is an identity permutation. That is alpha is an identity permutation. Identity permutation. And we have that an identity permutation is a one cycle. So in this case, alpha is a one cycle, because when alpha does not move any point, that means alpha fixes everything. So this kind of a permutation is an identity permutation, and identity permutation is just a one cycle. Now assume that k is positive. So assume k is a positive number. So that means the given permutation alpha moves at least one point. So let I1 be the point moved by alpha. Be the point moved by alpha. Now we define. Now since I1 is a point moved by alpha, define I1 is equal to I2. Then define alpha of I2 is equal to I3, and so on. And alpha of IR is equal to IR plus 1, where the point R, where the number R, where R is the smallest integer, for which IR plus 1 belongs to the set I1, I2, so on IR. We are able to say that we are able to choose this R to be the smallest integer for which this IR plus 1 belongs to the set, and it comes from the fact that the symmetric group Sn has been defined on a set that contains n elements only. So this means that the sequence of this list of numbers I1, I2, I3 up to IR plus 1, this sequence must eventually terminate, or actually we can say that this sequence, this list of numbers I1, I2, IR plus 1 must eventually have a repetition, because the number of elements in the set X on which the symmetric group Sn has been defined is a finite set containing only n elements. So let's make that statement here. Since there are only there are only n possible values, n possible values, and there are only n possible values. Thus, the list I1, I2, so on, Ik, so on must eventually have a repetition. Must eventually have a repetition. So when it has a repetition, therefore, we will reach a stage where some alpha ik will be some I j, where j lies from 1 to r plus 1, 1 to r actually. So now what when we have a repetition, we have a claim here. Then we claim that alpha of ir, we claim that alpha of ir is equal to I1. So this is our claim. Now since we have a repetition, we are claiming that from repetition fact that alpha of IR will be a point which will be equal to I1. So this alpha sends this IR to I1. Suppose it not. Suppose otherwise. So otherwise means that we are supposing that this alpha of IR is equal to some ij, where j is an integer greater than 1. Suppose otherwise, that is, we are assuming that alpha of IR is equal to some ij, where j is greater or equal to 2, and in fact it must be less or equal to r, because at the earth stage we have a repetition. Now uh, so therefore we have alpha of ir is equal to ig, but from this construction, when we had written that alpha of I1 is equal to I2, alpha of I2 equal to I3, and so on, alpha of IR is equal to IR plus 1, and j is a number from the set 2 to r. Therefore, from this construction we see that, but we have like this, but alpha of I j minus 1 is also equal to ij. It is from this construction, because alpha of I1 is written to be I2, alpha of I2 is I3, and so on, and alpha of IR is equal to IR plus 1, and this j is a number lying from 2 to r. Therefore, by this construction, we have alpha of ij minus 1 is equal to ij. Now we can look at these two numbers, IR and ij minus 1. These two numbers are actually two different numbers, because this 2 is, because this j is less than or equal to r. Now let's make some things here. Since j is less or equal to r, this means j is less than r plus 1. So this actually implies that j minus 1 is less than r. So the final thing that actually we need here is that j minus 1 is not equal to r. So therefore, the 2 points IR and IJ minus 1 are two different points. Therefore, and we are having here that alpha of IR is equal to IJ and alpha of IJ minus 1 is also equal to IJ for two different points IR and IJ minus 1. This means that the mapping alpha is not an injective mapping. So there, which is actually a contradiction, but since our because our permutation alpha is a bijection. Now, since we write these things here now, since j is less or equal to r, this implies j is less than r plus 1, that is j minus 1 is less than r, that is j minus 1 is not equal to r. So this not equal to r actually means that so this implies that 2 points IR is not equal to IJ minus 1. Thus we have a contradiction. Thus there is a contradiction. Thus um, we have a contradiction because alpha is a bijection. So therefore we must have we must have alpha of IR. Therefore we must have alpha of IR is equal to I1. Now let sigma be a cycle. Since we had defined this alpha of I1 is equal to I2. Okay, so we had defined alpha of I1 is equal to I2, alpha of I2 equal to I3, alpha of IR equal to IR plus 1, and now we are proving that alpha of IR is equal to I1. So that is now we will write this sigma is equal to in the form of a cycle I1, I2, I3, so on IR. Now, if so, sigma is this R cycle. If R happens to be equal to n, then the chosen permutation alpha, this is equal to sigma. So therefore, in this case, this alpha is a single cycle. So therefore, if R is equal to n, then alpha is a single cycle equal to sigma. But if R is less than n, then sigma, this R cycle sigma fixes all points in the set X minus I1, I2, IR. So if R is equal to n, then alpha is equal to sigma. That means the permutation alpha is a single cycle. But if R happens to be less than n, then the sigma fixes all points in X minus I1, I2, IR, where X is the original set on which the permutation group Sn has been defined. Now choose a permutation. Now we choose a permutation alpha dash belonging to Sn such that alpha dash fixes all points in the set I1, I2, IR and agrees with alpha on the set x minus I1, I2, so on IR. So this means that whatever is the image of points in this set under alpha, the same image is given to the points under alpha dash, but alpha dash fixes all the points in the set I1, I2, IR. So, and we note that this means that this gives us alpha is a permutation which can be written equal to sigma into alpha dash. Now sigma is a permutation which is actually a part of permutation alpha, where which is actually now an R cycle and it moves these points. Now alpha dash is a permutation which fixes everything in this x minus, which fixes everything in this set I1, I2, IR and agrees with alpha on the set x minus this thing. So this means that the permutation alpha can be written as sigma into alpha dash. Now since this point R it is less than n, this and it is this sigma is not a one cycle, therefore it contains at least 2 pointers. This means that this alpha dash is a permutation which is smaller than alpha. Thus by induction hypothesis, then clearly by induction hypothesis, thus by induction alpha dash can be written as the product of disjoint cycles. So here what we have actually done, we have broken this alpha as a product of two permutations. One is the cycle and another is a permutation, but now since its length will be less than the since the number of points moved by this alpha dash will be less than the number of points moved by the permutation alpha, therefore we can use the induction hypothesis on this alpha dash and write that alpha dash is the product of disjoint cycles. So this combining these two things, that sigma is also a cycle, thus finally we conclude, thus we have alpha is equal to sigma into beta 1 into beta 2 so on into beta suppose k as the expression of alpha as product of disjoint cycles, as product of disjoint cycles. So this proves the result that every permutation in Sn is either a cycle or it can be expressed as a product of disjoint cycles. Now in the previous lecture we had already shown that every cycle can be written as a product of transpositions. Now here we make one more statement theorem, so or we can let's write it as a theorem. Actually it is an easy result. Every permutation alpha in Sn can be written as product of transpositions. So every permutation can be written as the product of transpositions, and the proof comes from the fact. So proof is actually extremely easy. The proof comes from the fact that every permutation in Sn can be written as a product of disjoint cycles, and in the previous lecture we had already seen that every cycle can be written as a product of transpositions. So when we write every permutation as a product of disjoint cycles, then write all of those cycles as a product of transpositions, we finally arrive at writing every permutation in Sn as a product of transpositions. So the proof follows from above theorem and the fact that every cycle, or we can write every R cycle, is the product of R minus 1 transpose. Okay, with this result, we conclude this lecture here.